Gentlemen, welcome back. Today we're going to talk about the solution process. Now, just going to let you know this is going to be a longer video with a lot more notes and examples on the solution process. So be prepared. Here we go. So, solution formation. The compositions of the solvent and the solute determine whether or not a substance will dissolve. The three factors that affect how fast a substance dissolves include agitation, temperature, and particle size of the solute. So agitation. If the contents of a glass are stirred, the crystals dissolve more quickly, right? They're agitated. Right? Just think if you have a younger brother or sister. The more they mess with you or touch your stuff, the more you get upset, the quicker you get agitated, the quicker you get upset. So the dissolving process occurs at the surface of the sugar crystals. Stirring speeds up the process because fresh solvent, the water, is continually brought in contact with the surface of the solute sugar. Okay, agitation, stirring or shaking, affects only the rate at which a solid solute dissolves. It does not influence the amount of solute that will dissolve. An insoluble substance remains undissolved regardless of how vigorously or for how long the solvent-solute system is agitated. So temperature. So for example, sugar dissolves much more rapidly in hot tea than iced tea. Just think of in terms of you're trying to get in shape, right? When it's hotter out and you're working out, okay, the likelihood of you burning more calories when you're moving around, running, playing a sport is a lot more likely than if you're sitting not doing anything. So at higher temperatures, the kinetic energy of water molecules is greater than at lower temperatures, so the molecules move faster. The more rapid motion of the solid molecules leads to an increase in the frequency of the force of the collisions between the water molecules and the surfaces of the sugar crystals. So the rate at which a solute dissolves also depends upon the size of the solute particles. So the smaller particles in granulated sugar expose a much greater surface area to the colliding water molecules. So the dissolving process is a surface phenomenon, and the more surface area of the solute that is exposed, the faster the rate of dissolving. Now that's a lot of stuff right there in those 7 slides. So a little checkup here. Which of the following it will not speed up the rate at which a solid solute dissolves? So we talked about increasing temperature is definitely going to speed it up, so that can't be it. Stirring the mixture, we said agitation is going to do that. Crushing, it's definitely going to speed it up. The only one that logically could be decreasing the temperature. All right, so now, solubility. This is a review from last unit. Not last unit, we'll say chemical reaction, so 3 units ago. So we have these 2 definitions. Soluble, able to be dissolved. And we remember that state of matter for something that's dissolved, and that is aqueous, so AQ. And something that's insoluble, unable to be dissolved, right? A lot of times we talk about a precipitate, a solid. So, what is happening in this figure? And we'll get to this as we go along the next few slides. So we see here in this picture, we see first off our solute here, NaCl. And this blue substance, which we know is the universal solvent, which is water, right? And we see these ions breaking apart. Okay, so what is happening in this figure, right? We're showing a little bit about solubility. And this NaCl solution is dissolving in water, right? Soluble comes from the word solubility, able to be dissolved in water. Okay, so now we look here. So particles from the solid into the solution. So some dissolved particles move from the solution back to the solid because these two processes occur at the same rate. No net change occurs in the overall system. When no net change occurs in the overall system, we have a saturated solution. So saturated solution, the maximum amount of solute for a given quantity of solvent at a constant temperature and pressure. So this means no more solute can be dissolved in the solvent and the solute will settle. So, simpler terms, when you have a saturated solution, solute equals solvent. Done. So the solubility, so first off, in a saturated solution, a state of dynamic equilibrium exists between the solution of any undissolved solute provided the temperature remains constant. That's what I just talked about in green on the last slide. Solute equals solvent. We'll talk about equilibrium later on in the year. So the solubility of a substance is given the amount of solute that dissolves in a given quantity of a solvent at a specified temperature and pressure to produce a saturated solution. So solubility is often expressed in grams of solute per 100 grams of solvent. So grams per 100 grams of water. We're going to do a calculation in a few minutes, and this is going to be very, very important. So sometimes the solubility of a gas is expressed in grams per liter of solution. Once again, we're going to do a calculation to this later today, and this is going to be also important. So now, a solution that contains less solute than a saturated solution at a given temperature and pressure is an unsaturated solution. So, we have an unsaturated solution. Solute is less than solvent. Okay, pretty sure everybody's had a sports drink in here. And when we've maybe made our own Gatorade or iced tea or things like that, and we don't put enough of the mix in, there's too much water, right? That's an unsaturated solution. And we'll get to this in our third video. This is a dilute solution. So, if additional solute is added to an unsaturated solution, the solution will dissolve until the solution is saturated, right? So we need to add more solute to make that saturated. So we look here. The solubility of a substance is often expressed as which of the following? So it says grams of solute per 100 grams of, per 100 liters of solvent. Okay, so they basically said this, grams per 100, I don't know, my thing is acting up. Right here we have gram per centimeter cubed. I don't think we're talking about density though. Now we have grams of solute per 100 grams of solvent. And grams per 100 grams of solution. So the key thing here is we're both in grams in the numerator, so that's not going to help us out at all. Look at our denominator. I didn't see anything about 1 centimeter cubed on the other slide, so I'm not going to worry about that. The only thing I saw on the bottom, I saw 100 grams, and I saw 100 grams of our solvent. And what solvent did they use? Water. Since water is the universal solvent, not to be C. We're getting there, almost done. Okay, so solvent-solute interactions. Solubility varies greatly with the type of compounds involved. So like dissolves like is a rough but useful rule for predicting whether one substance will dissolve in another. So what makes substances similar depends on type of bonding, so ionic, covalent, polarity or nonpolarity, and the intermolecular forces between the solute and solvent. So, some factors affecting solubility. Temperature affects the solubility of a solid, liquid, and gaseous solute in a solvent. Both temperature and pressure affect the solubility of gaseous solutes. So here, the temperature, the solubility of most solid substances increase as the temperature of the solvent increases. For a few substances, solubility decreases with temperature. And one here would be YB2SO43. And NaCl is pretty flatline, but all the rest of them, see, they go up. Now, we're going to use this quite a bit. This will be part of a lab activity and along with your assessment for this video. So we have our substances, our formulas, solubility grams per 100 grams of water, right? Grams of solvent. And we have the solubility depending on what temperature is present. So we're going to learn how to do a couple calculations with these. Okay, so sorry I had to run and get my calculator. So now we look at this problem. And it says, what mass of AgNO3 can be dissolved in 250 grams of water at 20 degrees Celsius? So this will be a dimensional analysis problem. The key thing here is we need to locate, and we'll start this problem out. I'm going to have to flip to the next slide though, previous slide, to get this started. So we have 250 grams of water. So that's what we start with. We want to go to grams of AgNO3. And the grams of water have to be on the bottom. So our key thing here is we need to look at AgNO3, silver nitrate, and 20 degrees Celsius on our solubility chart. So if I do that, don't mind the mess, and I'll erase this. Okay. So we look. Remember we needed AgNO3, silver nitrate, at 20 degrees Celsius. And that was 222 grams over 100 grams of H2O. Okay, so we have 250 grams of water times the 222 grams of AgNO3 all over the 100 grams of water. So it's a one-step dimensional analysis problem. And you just have to look at your chart to find your numerator value. Your numerator value, only value that will change. So we have 250 times 222 divided by 100. Getting ahead of myself. And I get 555 grams of AgNO3. And that's as hard as these problems get. Keep following along. You're doing great. We're getting there. Okay. So now, supersaturated solution contains more solute than can theoretically hold at a given temperature. So the crystallization of a supersaturated solution can be initiated in a very small crystal called a seed crystal of the solute is added. So this is beyond saturation. When the solvent is heated, more solute can be added. Then allowed slowly to cool gently. This is unstable. Sorry, these are more than one bullets here. So this is one here. If you shake or stir, they crystallize. So here is when your solvent is greater than your solute. So here's a picture of this. So we see the rate at which excess solute deposits upon the surface of a seed crystal can be very rapid. So the first one here, the solution is a clear before a seed crystal is added. So here is when the seed crystal begins to form immediately after the addition of the seed crystal, and here is when the excess solute crystallizes rapidly. Can anybody tell me how or what operation or method we would use to get this solute out of the solvent? One would be filtration. Okay, so the effect of temperature on the solubility of gases. In liquid solvents is opposite that of solids. So the solubilities of most gases are greater in cold than in hot. So the polarity of water molecules plays an important role in the formation of solids of ionic compounds in water. So the slightly charged parts of the water molecules attract the ions and the ionic compounds and surround them, separating them from the crystal surface and drawing them into the solution. This solution process with water as the solvent is referred to as hydration. The ions are said to be hydrated. You could think of this in terms of us, humans. When we get more water intake into our cells, we become hydrated, right? It's the process of hydration. And that's all this shows in this next slide about the ionic solute of lithium chloride. So when lithium chloride is hydrated with water, it becomes hydrated. So nonpolar solvents. Ionic compounds are generally not soluble in nonpolar solvents such as carbon tetrachloride and toluene. The nonpolar solvent molecules do not attract the ions of the crystal strongly enough to overcome the forces holding the crystals together. Ionic and nonpolar substances differ widely in bonding type, polarity, and intermolecular forces, so their particles cannot intermingle very much. Oil and water do not mix because oil is a nonpolar, whereas water is polar. The hydrogen bonding between water molecules squeezes out water. Oil molecules may come between them. Two polar substances or two nonpolar substances, on the other hand, form solutions together easily because their intermolecular forces match. Liquids that are not soluble in each other are immiscible. Very important. And liquids that dissolve freely in one another are called miscible. So here's just a review. Types of solutions, solid and liquid. The next one, gas and liquid. We're going to talk about this one more in depth in a few slides. Liquid and liquid, and we talked about miscibility. Be able to mix. Immiscible, you will not mix. Liquid and gas, it's like humidity in the atmosphere. Gas and gas is your atmosphere. Solid to solid is an alloy, mixture of metals. And liquid to solid can be like a dental filling. And we will take a pause in the action here. And we will look for part 2 of the solution process momentarily.